All right. Good afternoon, everyone. This is back to back for me, but here we go. Lecture 2, we're going to be talking about fossil fuel technologies. Okay, so fossil fuels, what are these? Fossil fuels are formed by the decomposition of dead organisms and exposure to extreme heat and pressure from the Earth's crust. Fossil fuels are typically characterized as compounds that have these very sort of high percentages of carbon. And I'm sure most folks have heard of these fuels. The most common are petroleum, natural gas, and coal. And these three kind of represents your liquid, gaseous, and solid forms of fossil fuels. So petroleums you can think of as crude oil and the derived petroleum products that come from these. So commonly gasoline and diesel, and a whole number of other byproducts. Natural gas, also known as methane, right? This is your gaseous form of carbon that typically is going to come with a whole bunch of other impurities, but of the three is probably the easiest to sort of isolate. And then you've got coal. So this is probably the commonly I would describe this as kind of the dirtiest fossil fuel, and it can be dependent on the type and quality of the coal, which we characterize typically into several different grades. So you've got lignite coal, bituminous, and anthracite. And that is the order in quality from lowest to highest. And we'll talk about what that means in a little bit. So fossil fuels, these are, we're going to first talk about fuels used for electricity generation. So coal versus natural gas, these are both most commonly used in electricity production. And you can see the chemistry of the molecules below here. So on the left-hand side is just an example of the type of like molecular structure you might see in coal. This isn't a representation that is meant to show, oh, all coal looks like this, right? It's typically characterized by these really long carbon chains, and lots of impurities in the sense that you've got non-carbon based molecules. So if I look closely, you'll see nitrogen commonly on these things, as well as sulfur. And that can lead to byproducts in the combustion process of the fuel itself. Natural gas, on the other hand, methane, so that's the molecule that you see on the right-hand side. CH4, pretty straightforward. Definitely a lot, let's say, quote unquote, cleaner than coal. But it does include lots of impurities when extracted in its raw form. So things like CO2, hydrogen sulfide, water vapor, oil, nitrogen, hydrates, hydrocompound, or other hydrocarbons. And so some processing is needed in order to get it as let's say clean as possible. Okay, in terms of energy, coal versus natural gas, um, the energy content. So when I was mentioning the quality of the coal from lignite, bituminous to anthracite, um, one of the characteristics of those different classifications is the energy content. So the lower grade ones typically will have more impurities, less carbon, which leads to lower energy density. So a kilogram of lignite coal will produce maybe half or even less than half that of your highest quality, let's say anthracite coal. And so you can see in the table on the left, there is quite a large range in energy density of the coal, again, depending on its grade. Natural gas is fairly constant. If you remember from last lecture, we did talk about this in terms of BTU per cubic feet. And so natural gas typically is about 1,000 BTU per cubic feet. There is some variation, again, depending on its density and the quantity of impurities within the gas, but you're typically going to get about 1,000 BTU per cubic feet, or about 37 megajoules per meters cubed. Total reserves of coal is something like 1.1 trillion tons, or about 33,000 exajoules. And natural gas, you've got about 205 trillion cubic meters, or about 7,600 exajoules. These are sort of approximations, and the numbers that the reserves refer to often changes over time. So, take these with a grain of salt, although it's not going to change dramatically, right? Your reserves might go up slightly, but generally, especially if we're talking about order of magnitude, it won't ever look too different from this. And to give some relative perspective, the worldwide annual primary energy consumption is about 500 exajoules. So that gives you some sense that, like, oh, if the entire world were just using natural gas or was just using coal, how quickly would we sort of use up all of our resources? There's a figure that folks like to show for your global energy demand, which is the blue sort of rectangle right up on top of this stack, compared to the resources that are available, which is slightly different from a reserve. But again, this chart is mainly meant to focus your attention to the sort of order of magnitude size of resources for our primary energies. And you can see what that looks like relative to each other. And annual solar energy is far and away the largest, right? But capturing it is a relatively inefficient process, and it's not like you could cover the entire globe in solar panels just to capture all of that solar energy. But it does point to the fact that there is a lot of it sustainably available. Okay, so let's go back to our fossil fuels and hone in on some of the processes and conversions related to it. Coal mining, so extraction of the primary coal resources. There are a number of different mining methods in order to get at that resource, and which you can see here. So you've got underground mining methods versus surface mining methods. So underground typically you're either drilling down or drilling straight through or drilling in a slope, but basically creating these tunnels to extract your resources, as you can see on sort of the left side of the chart. An alternative to this is surface mining methods, where essentially you are digging away at, let's say, this mountaintop, or some other type of resource-rich area. You are basically getting rid of the land surface in order to get to your coal resources. And you can see the sort of different types of mining that can happen in those processes as well. One of the big complaints of these types of mining processes, especially from the surface-based strip mining, is that you're getting a lot of sort of localized environmental damages. So we do, I think, in the field of like climate change, we often think of coal as being bad for all of the greenhouse gases that it's emitting. But it's important not to forget the sort of environmental consequences from resource extraction as well. Okay, what about for natural gas? So natural gas resource extraction, we can kind of divide into two types. One is known as conventional, and the other as unconventional. So you can see conventional gas extraction looks something like this, where you have pockets of gas that you can drill basically straight into in order to extract. And that had been common for many decades. But more recently, kind of in the mid 2000s, the unconventional extraction methods became quite a bit more popular. And so some of you may have heard of this, known as shale fracking. And that really kind of opened up the sort of reserves and resources available in many different parts of the world to extract natural gas. And in fact, in the US, the US turns out to be a really good, rich area for shale fracking. And then that actually was a very large sort of transformation to our energy system, so much so, right, that it turned the US into a gas exporter as opposed to a gas importer, and had big consequences to the operation of our power system, which we'll get into in a little bit. Fracking, the actual process of fracking comes from the term hydraulic fracturing. And the way this works is, instead of going straight down, they drill sort of horizontally across a whole bunch of fissures. And that opens up this network of cracks that allows gas to flow into the pipe, which can then be eventually extracted. One of the big worries and drawbacks of this process is that it can lead to instability in the land itself, right? There's some research that has shown hydraulic fracturing has led to certain negative outcomes, like earthquakes. That was really common, I believe, in Oklahoma like a decade ago. It can lead to methane leakage during the mining process, which is a big worry, and particularly bad for climate change. And the other really big one is wastewater. And so you could have leakage of liquids from the fracture zone, although that is typically considered less likely. But this process, as you can probably see, uses a substantial amount of water, which can't be sort of reused afterwards. And so a lot of the wastewater is had been historically poorly managed, or injected back into like storage wells, or injected into deep storage wells, which could then leak. And that led to lots of bad outcomes, especially if it gets into like groundwater systems and your water table. So there are a number of sort of negative outcomes that have been associated with hydraulic fracturing. Okay, thinking about the economics between the two fuel types, so coal versus natural gas. So this is a little bit older chart, but typically the story that we want to tell here is that the price of coal delivered over the last decade compared to the price of natural gas is quite different. So coal typically, a lot of coal prices ended up getting quite a bit more expensive after the discovery of fracking, due to the economics of sort of price competition between the fuels in electricity production. So fracking really sort of decreased prices in natural gas, which led to less usage of coal over time. The processing of these two fuels is fairly different. So for coal, essentially what you want as an input into your power plant is basically this coal dust, where you sort of grind it up as fine as possible to facilitate the combustion process. This is a little bit different for natural gas, where you want to clean up any of the byproducts within the extraction process as much as possible, right? And so from your either gas well or oil and gas well, you have to separate your oil and water, getting your a more pure stream of gas. You want to be able to refine that to remove any byproducts. It goes to a compressor station before ultimately getting delivered to your end consumers or power production units. And so natural gas processing and distribution is a little bit more tricky than coal typically. So fossil fuel combustion, in order to take advantage of the fuel, essentially at some point you combust it, and we'll talk about why and what you get out of it, out of the combustion process in a little bit. But generically, we can actually take any hydrocarbon and combust it through a chemical process by combining it with oxygen and heat. And that will produce carbon dioxide and water. And as an exothermic reaction, you get a lot more energy in the form of heat out of it than you put into it. And that is naturally how we're going to take advantage of the fuels. So this equation is a lot simpler for natural gas, which is just CH4, right? And that process looks something like this if I just plug that into our equation from above. But when you have impurities within this combustion process, you can have emissions that aren't just going to be carbon dioxide and water. You can also have nitrogen oxides if you have nitrogen presence. You can get carbon monoxide through incomplete combustion. You can also get the initial input product itself, methane, if it's not fully combusted. And then you can get a bunch of particulate matter, nitrous oxides, VOCs, sulfur dioxides. And these are typically more negative outcomes for air quality. Coal is similar in a sense, but you get a whole bunch more byproducts typically. So you can actually write the equation, right? The coal compounds are not like a homogeneous molecule. It's just big hydrocarbon with a bunch of impurities in it. And when you combust coal, that includes a lot of those impurities, you get all of the bad things from that you see up in natural gas, and you'll get a lot more things like sulfur oxides compared to natural gas, but you can also get a bunch of solids, right? And so these items that I'm listing here are very common byproducts of coal combustion. So fly ash, flue gas, bottom ash, boiler slag, a lot more sulfur dioxide, but you also get like heavy metals, mercury and arsenic. It's pretty bad stuff all around as far as emission like byproducts go. Okay, and so combustion, the whole point of combustion of these fuels is to extract energy of some kind. And we'll talk about the concept of how that happens. And then we'll look at some actual sort of applications of capturing energy. We can think about this in terms of heat engine cycles. So we think about this, this is also known as kind of a thermodynamic cycle. And all that is you have some mechanism that has some initial state. It proceeds through a series of states and returns to the initial state. And the whole point of this system is that as you go through the cycle, it can perform some work on its surroundings. And so we are going to take advantage of the combustion to sort of perpetually do these cycles to extract as much energy as possible. So the theoretical sort of maximum energy that you could get is known as a Carnot cycle, and we'll look at that in just a second. This is a theoretical type of system that you can't actually make. But then we will look at some of these other cycles, Rankine and Brayton cycles, to get a sense of what these look like in reality. So Carnot cycle, upper limit on efficiency that you can achieve in a thermodynamic cycle. Again, this is a theoretical construct. And if your starting state is something like this, these are the sort of cycles that you move through. in order to extract energy, and the energy and work, which is moving this sort of piston sort of up and down. And the whole point of the thermodynamic cycle, again, right, is that you can do this and return your system back to its first stage. So you go one, top left, top right, bottom left, bottom right, and then back over to top left. So what's happening here is that you have essentially a hot reservoir and a cold reservoir, and the thing that you're exploiting is essentially the movement of heat from hot to cold, and you're doing it in such a way that you are kind of losing the least amount of energy as possible. So the hot reservoir puts heat into your central system, which then through isothermal expansion moves your piston upwards. The piston continues to move upwards through adiabatic expansion, and then the heat within the system moves into the cold reservoir, and you get isothermal compression, followed by adiabatic compression, moving you back to the first stage of the Carnot cycle. And the reason why this is not really possible is that you can't get sort of perfect isothermal and adiabatic expansion or isothermal and adiabatic compression in each of these stages, right? You're going to be constantly sort of leaking heat across the system. And so you can't really build this type of system in practice. But we can take the concept of the Carnot cycle and apply it to some systems to try and extract as much energy as possible. Okay, and so what is the type of work that we would like to extract from these systems? So it turns out, so if you brush up on your electricity and magnetism, right, the thing that we want to get out of the combustion of fossil fuels and, let's say, the production of movement is the generation of electricity. So the way this works is a generator can convert mechanical energy into electrical power. A motor, a generator, actually, and a motor is an example of this type of system where you have two primary components. You have a rotor and a stator. So the rotor is the part that rotates. The stator is the stationary part. Not too hard to remember. And essentially the way electricity is produced is that you have this wire that's spinning in between two magnets. So inside of an electric magnetic field. And so whenever you have a coil moving through a magnetic field, it induces current to be created through the loop here. And what ends up happening is if I just spin this loop over and over again, that's going to continue to induce electrons to move through this circuit. And so the basic punchline here is that spinning things creates electricity. And the vast majority of all electricity that we consume today essentially comes from spinning something, some type of turbine, with the exception of, let's say, solar, which doesn't actually require any sort of mechanical energy, but basically everything else does. So the way the the type of sort of generators that we typically extract that mechanical energy is known as a turbine, which is the thing that will spin the coil or the magnets in a generator. So we extract energy from fluid flow and convert it to work. These are some examples of turbines. You can see, so a bunch of different types of turbines: steam turbines, gas turbines, water turbines, wind turbines. We can see here, if you, in an impulse turbine, if you introduce like a fluid flow, here you can see how you're spinning the rotor, right, by pushing these blades. And the way that this is arranged is that you have fluid flowing through some nozzle that then hits your blades to then spin your turbine. And there are slightly different configurations of how to do this, right? And that can be optimized to specific types of fluids and flows. So we can see what that looks like in a modern steam turbine. You can see that there are like many stages of these blades. And so if you think about why that is, one analogy that I like to make is, if you have one of those spinning fans that you blow, and you blow at it and it spins around, if you put your hand behind it, you'll notice that there's still air sort of moving. And so if you lay out some sort of multiple rows of that, the blades will spin progressively kind of slower behind it, but you're capturing more of that energy moving through. And so that's the idea here, is that you are propelling some kind of like fluid flow through the turbine, and you have multiple stages of fins to capture as much of the energy as possible. Okay, and so in a steam turbine, maybe obvious from the name, essentially what you want to do is you're sending sort of hot pressurized steam through the turbine in order to spin your generator to produce electricity. So what does that look like? In this diagram here, this is known as a Rankine cycle, where I have a pump that essentially pumps water into a boiler where it gets turned into steam. That steam gets sent through your turbine to spin it and produce electricity. And the steam then passes out of the turbine into a condenser, which goes back into water and gets sent back through the pump into your boiler, and so on and so forth. So this is your thermodynamic cycle, where I can reset myself back to an initial stage and can go through this process again. So the maximum theoretical efficiency that you can get out of the Rankine cycle has been estimated to be at about 64%. But today, the highest efficiencies that you're going to see in sort of contemporary coal plants is closer to about 40%. And even that would be, I would argue, kind of on the high end for that would be a pretty sophisticated coal plant that's getting a 42% efficiency. So this diagram maybe walks us through what a typical sort of plant looks like. So as I talked about before, you first start with your coal input, which then gets processed actually usually at the steam plant itself. So sometimes these will be connected directly with the railway, where a rail car is going to come by to the plant and it opens the bottom up and it drops all the coal directly essentially directly into these mills that then crush down the coal into a powder. That increases the surface area, which allows for better combustion to happen. And so as the coal gets passed into the furnace, this allows you to combust it. You get solids typically falling down into the bottom pit. And then you have byproducts of your combustion, gaseous byproducts going out of the chimney stack. Okay, and so what you can see in this, in sort of parts 3 and 4, 3, 4, 5, is the Carnot cycle sort of being displayed within this diagram. So you have water in this closed loop going into this turbine. And then that's going to spin and allow for work to be done out of the generator to produce electricity. And if you look closely, you're going to see that the water that then gets passed to the condenser back into the furnace is in a closed loop. So why would you do that? The reason for that is the water that you're putting into the turbine can then be like a very pure stream of water without the possibility to introduce any sort of contaminants, or for you to, or I should say, and this allows you to not have to purify and refine your stream of input water because you're using the same water sort of over and over. The condenser is cooled by non-purified water. And so typically you're going to see these things sitting at a river, and you can just use that water in the open system to cool down the water sort of coming out of your turbine. That water is then, as it cools, as it warms in order to cool the water coming out of the turbine, that water can get evaporated through a cooling tower. So actually, when you look at a steam plant, you typically are going to see something like this, where you have these cooling towers and you have this chimney stack. So the cooling towers typically are going to actually be pretty safe in terms of the like the stuff coming out of that tower. That's all usually just water vapor, and that's typically a lot lower to the ground compared to chimney stacks, because the chimney stacks themselves have a lot of filters and technologies to try and remove as many of the gaseous bad byproducts as possible. Right? A lot of that is actually mandated through regulation, and so these things are going to be the chimney stacks are going to be way taller than the cooling towers on average. Yeah, and so that's kind of the basics of how your steam plant works. And we're gonna look at a bunch of other different types of power plants, but for the most part, they're gonna look something like this. And again, at the end of the day, the name of the game is, as long as you can get something to spin, you can produce electricity. So that is going to be the main objective of most of these plants. Okay, what about gas turbines? So these are not the same thing as a steam turbine, and we'll see why in just a moment. There are 3 main components of a gas turbine. So you've got your rotating gas compressor, and so all of this stuff at the front here is meant to essentially compress your gas input, and then you have a downstream turbine that's on the same shaft, and then you have a combustion chamber in between your in between your upstream gas compressor and your downstream turbine. So what ends up happening here is that you essentially combust your natural gas, which is going to cause this whole contraption to spin, right, which produces electricity as it's connected to a generator. And you get these really, really hot combustion gases coming out of the end of your gas turbine. And in fact, if you kind of look at this diagram and you're like, hey, this looks pretty familiar, right? That's because that's exactly what conventional aircraft use in order to fly. This is essentially the same thing as a gas turbine, and you're not leveraging all of the electricity production, but a lot of the thrust is being produced by the hot gas that's getting shoved out of the back of the turbine. And in fact, you could easily rip the gas turbine off of an airplane and just stick it into, I mean, you'd need a little bit of modification, right? But you could take that turbine right off of an airplane and stick it into a power plant if you wanted to produce electricity. That would work essentially no problem. But you probably wouldn't want to do the reverse. That probably wouldn't work out very well. Okay, so the natural gas turbine uses what's known as the Brayton cycle. You have fresh air coming into your compressor, fuel getting added, you get your combustion happening, spinning your turbine, and then your gases are exhausted, and the work is being performed by spinning this, right? And you can see this is kind of the general diagram for the Brayton cycle. But the efficiency in practice is around high 40%. The maximum ones that you'll see can even reach above 50%. So these things are actually quite a bit more efficient than coal plants. But really, where you're getting the biggest benefit is in a process known as combined cycle. This is where, as I was mentioning, going 2 slides back, so you're producing a lot of heat, a lot of excess heat out of the byproducts of combustion shooting out of the turbine. And so it turns out you can actually take advantage of that. If we look at this diagram here, you can see your Brayton cycle gas turbine right here in the gray and yellow. And your hot exhaust gases can actually be used to heat water. And that can then be used to power a steam turbine. And so combined cycle uses both the Brayton and the Rankine cycle in a single system, where your gas turbine boils water through its exhaust heat byproduct that then goes into a steam turbine to power a different generator. And so by capturing the excess heat there, your efficiencies can get even higher, right? You can reach something like 60% efficiency. And so this process really lets you really lets you compete favorably against your sort of traditional like steam turbine. And the layout of a natural gas, like a combined cycle plant, might look something like this, where you've got both your steam turbine and your gas turbine working together in a combined cycle system. If you ever have a chance to go visit one of these, I highly encourage it. Pretty interesting to see how your electricity is being produced. I would recommend bringing earplugs. It is very, very loud. In fact, I think they're not even allowed to turn it on all the way up if you are within a certain distance without ear protection. Okay, so we've talked about some of the most common sort of fossil fuel electricity production power plants in the US. And this chart is to give, some kind of a spatial overview of that power production. This includes all types of power plants, though. So the color of the dots indicates the fuel type, and the size of the dot indicates the capacity. So the larger the dot, the more electricity it can produce at any given time. What you'll see on the West Coast, and particularly in California, you'll see that there isn't any blue coal. Well, there is actually one blue dot right over here, if you're able to see my cursor in sort of Northern California, although that one doesn't really produce any much power anymore. But most of the West Coast here, you're going to see lots of pink, which is solar, and a lot of purple, which is natural gas. Up in the Pacific Northwest, the most common power production is from hydro, and so you see a lot of sort of larger green dots up in the Pacific Northwest that's providing that power generation. You start to see quite a bit more coal plants in blue, sort of in the Midwest and East Coast. There is a large swath of gray, kind of in the Midwest as well. Those are wind farms, and the Midwest tends to have the best resources for wind, so it makes the most sense to put them there. And the last one that I'll point out are orange dots, which are nuclear power plants, of which you can see them sort of interspersed, particularly throughout the East Coast. There is one orange dot in California. This is the Diablo nuclear power plant, which was slated to be shut down in 2025, but its life actually got extended last year. It's actually, or not last year, sorry, no, that would be last year. It's 2023. A couple months ago, pretty recently, they decided to extend its lifetime. And we'll talk about implications of nuclear a little bit later. So whether you're sort of for or against it, just note that particular power plant is still going to be open for a little while. Okay. Utility scale generation capacity by initial operating year. So the chart on the left shows when power plants essentially were installed in the US. We can see that there was sort of a large growth in power plants in the 70s, um, leading up to the 70s and sort of declining slowly over time. And that involved a lot of big coal power plants, as you can see in the brown, as well as nuclear power plants getting installed in the 70s through the late 1980s, early 1990s. But since then, essentially no nuclear has really been installed. The big growth in the 2000s was natural gas, and that is in no small part due to the fracking that we were mentioning earlier. And now we're finally starting to see sort of large growth in renewables, in wind in green, and solar in yellow. And you can see the overall capacity of these different fuel types based on the different colors that you can see here.
Alan, I have a question.
Yeah, go ahead.
Was all the capacity built between 1970 to 1980 retired when there was the peak in natural gas power plants in the early 2000s?
A decent chunk of it was, but not all of it. A fair amount of generation gets retrofit and the lifetime extended. So to the extent where that is sort of possible and economically viable, then oftentimes that was done. But yeah, that is a good point. So that the typical lifetime of a lot of these plants, you're usually talking about on the order of like 30 years, right? And some can be a lot longer, some can be a little bit shorter. And so you do have these sort of corresponding peaks as some of this stuff gets retired. Yeah. Okay, really sort of basic layout of the grid. From there, your power generation then goes through transmission and distribution. So long distance movement of electricity from your power plant to, let's say, a city would require these sort of high voltage transmission lines. So these are the big metal towers that you'll see when you're like driving on the freeway. The higher voltage lets them transfer the electricity at length with lower sort of losses. These then go to these sort of local substations that reduce the voltage. And then these are your distribution systems, typically are where you see, those wooden poles with power lines that go into your end services, commercial, industrial, and residential customers. And so that is how the sort of nature of the grid is interconnected through everything connected all the way back to the power station and connected up to your home. This type of system, I don't know if the right word is to say sort of challenge, but you can see a little bit of breakdown in this typical standard layout as you have sort of more distributed energy systems where you actually have power production, right, happening sort of more at the end stages as opposed to this like big upstream thing. So you can think about like solar rooftops, and even there are some small example cases of like disconnected systems that allows you to cut away the rest of the infrastructure, right? Generation, transmission, and sometimes even distribution, for these like localized, like microgrid type things where you're generating very near to where the power is being consumed. Okay, last thing that we'll talk about is environmental impacts. So the big one is carbon. Thinking about impacts on climate change, the carbon cycle refers to kind of the exchange of carbon in throughout our sort of ecosystem. So there's a balance between what we breathe and what gets taken up by photosynthesis, right? So when we breathe, we exhale CO2, but in photosynthesis, CO2 is taken in and additional energy sort of is added to create sugars and that sort of thing, right? And so generally in the natural cycle, these things are balanced and you have a similar type of quantity being exchanged in the ocean as well. And where you start getting some issues is through anthropogenic emissions of carbon, where you release carbon into the atmosphere, but the sort of equivalent balancing uptake of CO2 doesn't really exist. And so that leads to a non-steady state cycle where emissions are continuously sort of building up in the atmosphere, and that is ultimately leading to the issues we're trying to combat related to climate change. The sort of very rough rule of thumb that I give is, again, roughly speaking, you are talking about on the order of like 20 gigatons annually of CO2 going into the atmosphere and out of the atmosphere sort of naturally, and then another additional 20 to 30 gigatons of CO2 that's going sort of anthropogenically emitted into the atmosphere. Okay, the last thing that I'll talk about in relation to sort of the emissions, I think it's kind of an interesting food for thought here. So one of the biggest, again, I'll highlight one of the biggest things that happened in the US as it relates to fuel use was the sort of takeover of electricity production coming from natural gas, again, as a byproduct of the fracking that has sort of opened up natural gas resources in the US that has really started to dominate electricity production, replacing coal at sort of a one-to-one rate, which you can see starting to happen sort of in the mid 2000s. You can see coal decreasing in consumption and natural gas sort of increasing at the same rate that coal is decreasing. What that actually means is that coal emissions has decreased very substantially by over 700 million tons annually, while natural gas emissions has increased by about 300 million tons annually. And that is due to the fact that natural gas is just so much cleaner than coal. So when we think about emissions from these two types of power production facilities, coal is just about 2 tons of CO2 per megawatt hour, whereas natural gas is about 1 ton of CO2 per megawatt hour produced. And as actually much as we think about sort of a fossil fuel free future, right, in order to combat climate change, probably easily one of the biggest things in terms of emissions reduction over the last decade has basically been because of this switch that has really dominated a lot of the CO2 emissions reduction across all sectors in the US. And so, eventually we'll want to switch out of natural gas, right, to be a totally sustainable system in terms of emissions, but it has been quite a big boon in terms of decreasing emissions, because it has basically allowed us to switch away from coal, which is the one of the dirtiest things that we could do. Okay. I really flew through this lecture as well. It's much faster without any questions, but again, if you do have any, please feel free to post them online, and I will do my best to answer them as quickly as possible. Yeah, other than that, thanks for listening, and hopefully I will see all of you guys soon. Just as a quick reminder, the Monday of our second official week of class is a holiday, so we still won't be in person until Wednesday of the second week. All right, and with that, I wish you guys all the best until I see you all in person.